Hello, welcome to this video about the Lighthills wave equation. The idea of the video is to show you how to derive Lighthills wave equation based on the conservation equations, like the conservation of mass, the conservation of momentum. And this is without any limitations, so it holds. It simply reassembles the equations of fluid dynamics. We use, or Lighthill use there, the Reynolds form of the momentum equation. So here we have the momentum conservation in Reynolds form with the momentum flux tensor here, this pi tensor there, which is simply the following. If we assume an ideal linear acoustic medium, then the momentum flux tensor is simply the contribution due to the pressure, which can be reformulated as it is a linear acoustic media in terms of the density, as the primary quantity of Lighthill's wave equation is the density variation. Okay, based on this ideal linear acoustic medium, one can then go one step further. We say we have kind of this base condition that we have a linear acoustic medium with the momentum flux tensor, which is this pi null. Now the idea is we would like to compute sound which is generated by some kind of body of vertical structures, turbulence structures, some other fluctuations like density fluctuations, or simply some viscous stress distribution. So the sound generated by the turbulent structures in the real fluid is exactly equivalent to that produced in the ideal stationary acoustic medium forced by a stress distribution. This deviation to the stress distribution, pi minus pi null, is called Lighthill's stress tensor. And this Lighthill stress tensor is then a very prominent source term for air acoustics in Lighthill's analogy. And it is derived the following. We now use the adaptive momentum equation. So we have the momentum equation, which is this term on the right hand side, the pi term there in Reynolds form, and then we just simply add the acoustic base condition to it, which is this pi 0, and based on that we can reformulate the momentum equation. So the term on the left hand side is reformulated according to this, that we insert the momentum flux term of the linear acoustic medium, and on the right hand side we then insert definition of Lighthill's stress tensor. We do the same, or we insert the quantities defined here, the perturbation on the acoustic density. We insert it also into the mass conservation itself, as say that the ambient or the zero condition is 0, and then we can derive, as we did it before with the wave equation, in a more limited sense. So for the linearized wave equation, we can manipulate these two equations by taking the time derivative of the space derivative top equation and the time derivative of this equation, and then manipulate it together, and then we arrive at the Lighthill's inhomogeneous wave equation itself with the Lighthill's tensor as a source term. And this equation is then used for Lighthill's analogy, where he used Green's function, It can also be used in the finite element context, or as it was used by curl, which did some additional manipulations to the equation. To our knowledge, Lighthill's analogy is an exact reformulation of the fluid dynamics equation, so the source term not only accounts for the generation of sound but also for acoustic self-modulation caused by acoustic nonlinearity, convection and reflection of the sound waves by the flow, and attenuation by the thermal and viscous action itself. The main challenge of using Lighthill's wave equation and the formulation is that regarding the practical application, one needs inside the source domain and also in regions where acoustic nonlinearity, convective and refraction effects are present and so on and so forth, one must already compute the sound with the preceding fluid dynamic simulation in order to can replicate the acoustic signal using Lighthill's wave equation.